All right, we're going to look at some domain and range of different functions. So first we have the different ways you could see the relations. That would be either through ordered pairs, you've got here, or you could have a graph showing the same thing. You might also have the mapping diagram, and when you have this mapping diagram, you have your x values over here, your inputs, and then the arrows going over to your outputs or your y values. And so these just show up as ordered pairs. So 0 could go to -2, or 0 could go to 2, or 3 could go to -1 or 1, so on and so forth. So these are just showing you ordered pairs, really, just in a different way. Then you have a table where they're matched up, x values on the left, y values on the right. Or you could have it show up as an equation, such as the linear equation it's got here. So for your domain and range, your domain is always going to be your input values. So your input would be your independent quality, and that is your x values. So whatever the number is that's going in, that's your domain, your x value, and then your range would be your output or your y values. So when we're looking at domain, we're looking at x values. Range, we're looking for y values. So on number 1 here, it says find the domain and range of the relation above. So let's look at this function for e. The domain is just going to be those x values that we have. So x values would be 0, 3, and 4. We'll just copy that down here. Domain was 0, 3, and 4. And then my range is going to be my y values. So for this, we don't know the y values yet, but all we've got to do is plug in the different inputs that we have and see what our output is. So I'll plug in a 0 for x. So we'll do y equals 4 minus 0. It gives me 4. So that's going to be the first value of my range. Then I could plug in a 3. So 4 minus 3 would give me a 1. And then a 4. So 4 minus 4, 0. So those are the y values, or just the output, whatever the result was we got whenever we put those into the equation. Next thing we'll look at is deciding whether or not something's a function. So whenever it's a function, it just has to have, for every input, there's only one output. So if I put in a 0, I should only be able to get one number out. So when I look here, if I put in a 0, I could get a -2. Or if I put in a 0, I could get a 2. Same thing with 3. I could get two different numbers there. So anytime you have a repeating x value, that's going to mean no, it is not a function. For this one, if I put in a 1, I could get a 2, 2 a 2, 3 a 1, a 4 a 1. So I have similar y values, but since all the x values are different, that means yes, it is a function. For our mapping diagram, if I put in a 1, I see two lines coming out from that. So that means I could get two different outputs. So no, that would not be a function. And then for number 5, the table, I can just look quickly and see that all my x values are different. So that one would be a function. The last thing we'll do to decide if something is a function is a vertical line test if you've got a graph. So all that means is, if I can draw a vertical line up and down through this everywhere and it only hit one point of the graph, then it is a function. if I draw a vertical line through and there's a place where I hit 2 of those, then there's 1, there's 2, so no, that would not be a function. So for this one, number 8, it has those 2 points that are right there, so no, it would not be a function. Last part on this page is using that to find, using the function notation to find the value when x equals something. So all we do is it's got the f of x equals 5x minus 1, and we want the answer when f of x, when x is 10. So instead of an x, all I'm going to do is it says that x is going to be a 10. So in parentheses, I'll put a 10 there instead of the x value, or as the x value. So I'll do 5 times 10 gives me 50, minus 1 would be 49. So again, we just take and put that 10 in for the x. So same thing for this. It says f of x is 2 plus x squared. And we want to know what it is when x is negative 3. So it's like we're looking at that graph and saying, okay, when I go to the negative 3 spot for x, what's the y value? Is basically what we're doing. So that would be 2 plus negative 3 squared. So negative 3 squared would be 9. And just remember, if this is something that you put in the calculator for larger negative numbers, for instance, make sure that you have those parentheses, because if you square this without the parentheses, it's going to give you a negative number. You'll end up with the incorrect answer. So for this one, we get 11. And that is using our function notation to solve for a specific point. So if we were to look on the graph and look at where x was negative 3, you'd have a point where it hit of negative 311, and that would be the point that we were looking for in this instance. And the last part of this, we're looking at the entire domain and range. So for the first one, if I look, I'm going to try and put a point and label an ordered pair at the end of this graph somewhere, and I notice pretty quickly that, well, this one has an arrow, which means it keeps on going this way, so I can't put a point there. Well, it's got an arrow there, which means it keeps on going. I can't put a point there. So if they don't give us a place where there's an end point, that means, or if there's no, like it continues on, this one's going to the left and up on forever. This one's going to the right and down. So there are no constraints on that, which means it goes left or right, all real numbers. There's not an x value that it's not allowed to have. And the same for the y values. It goes up and down, on and on forever. So those y values, the range, would also be all real numbers. And since we got a graph, you can quickly check your vertical line test for whether or not it's a function, and we'd say yes, it is. Okay, for number 12, looking at the domain and range of this one, I do have a point on the left and on the right that it stops. So let's go ahead and label those points. This is at negative 1, 2, negative 6, negative 6, and then up should be 8. We got negative 6, 8, and then positive 6, 1. So I've labeled those 2 points just to give me an idea of where it starts and stops on both ends. So essentially what's happening is when I've got one continuous line like this, is I will label the domain with the x values, the smallest first and the biggest second. But as we're looking at the graph, can really kind of say, well, over here on this part, there's no part of the line that I can see. It's not till we get right here that I have part of the graph, and so it starts there where x is -6, and it ends all the way up here where x is +6. And I could have any of those values in between. I could have a -5, a 0, a 1.025. Any number in there is possible. So that means x, all of those x values have to be greater than -6. And we'll remember that when you've got an open dot like that, it just means greater than or less than. If it's a closed dot like we've got on the other side, it's going to be less than or equal to. So -6 is less than x, which is less than or equal to 6. Then we're going to do the same thing for our range, just looking from bottom to top though. So the lowest place it's at is at +1, and it goes from +1 all the way up to a +8. So that means our y values start here at 1 and go all the way up to 8. Again, that's continuous. And so we'll look, this dot where 1 is closed in. So that means it would be less than or equal to. And then up at the 8, it's open, so just less than. And we check our vertical line test to see if it's a function, and we can say yes, that most definitely is a function. Okay, this next one, number 13, looks a little bit different, but when we're looking at the domain, still kind of ends up the same. So let's label, see this point right here, I'm at -10, -2. And I'm just going to label this point right now, 1, 2, 3, 6, 4. So those are the 2 points, farthest left and farthest right, and kind of my top and bottom. But if you'll notice, this looks way different than the one before it. So as we're looking left to right, if we think about it, if you were looking down from the top of this, so if we were to rotate it up towards you and you were looking straight down and got rid of all the grid lines and everything, what you'd see was kind of like if you were looking straight down at steps that were all painted the same color, is that this line goes here, but then as soon as this one stops, it hops up to here, and then as soon as that one stops, up to here, and then same thing for that one. So if I were to move the lines down, you could think of those dots as kind of interlinking together. Basically what that means is whenever this one stops, this one begins right at that exact point. So this from left to right is actually continuous because there's nowhere where I would not have an x value. So starting at -10, as soon as I get to -6, -6 isn't included on this little segment, but it is included up here. And so we have a continuous flow all the way from -10 up to 6 there. And so we have -10, our domain is less than or equal to, because that was closed in, x. So all of my x's are in between -10 and a +6. Remember that dot is open, so it's just less than 6, just like so. Okay, now when I look at my range, this is where it looks even more different. So I'm still starting at my bottom. So my lowest value is a -2. My highest is 4. But if I'm looking at it straight this way, I have some gaps here. So I have a part of the graph at -2. I have a part of it at 0. I have part at 2 and part at 4. But in between that, there are these big spaces. So this actually would not be a continuous range because I've got these spaces in the middle. So when that happens, I'm just going to label the parts. And for this one, it's all of these y values would be 2, or negative 2. All of these y values would be 0. So if I was going and labeling each little point of this graph, the y values of everything here would be negative 2. Y values of everything here would be 0, then 2, and then 4. So for this one, it really, though it looks different, if I just think about putting a point in some different spots on here, I'll get a whole bunch of different x values, anywhere from negative 10 to 6, but I can only get those 4 y values. So we'll just write those 4 numbers as our range. And looking at our vertical line test, just notice that when we go through this point here, even though there's 2 dots, because one is open, it means that's not included. So yes, that would be a function. Okay, we'll look at one more real quick, just as a reminder on our absolute value. So when we do absolute value, you have y equals the absolute value of x minus 1. So as I work that out, remember whenever you have those absolute value bars, it turns anything that's in here from a negative to a positive. So really it just takes and it says the distance away from 0. So if I made x equal to 0, that would be a negative 1, which when I do the absolute values would change to positive 1. So let's just do a little chart here. X is 0, y would be 1. If I made x 1, y would be 0. And if I did 2, 2 minus 1 would be 1. And we could keep going. 3 would be 2. And so I end up with a graph that looks something like this. The absolute value doesn't curve around like a parabola. It just makes an immediate turn going from positive to negative, just like that. So I can look at my domain going from left to right. There's no place that it stops. I can't put a point here and say it ended there. So my domain for this would be all real numbers. My range, if I look going upward, I've got those arrows that could keep going forever. But going down, I do find a point here, a lower limit, where it's going to stop. And so that would be at 0. So we'd say all those y values are going up from 0, so they could be greater than, they could also be equal to, because right here I have a 0 on y. I'd say y is greater than or equal to 0. And I could check my vertical line test one more time. We'd say, yes, that was a function. So that is a lot of review information for you about domain and range and function notation.